Hey everybody, back for another round of astronomy. Awesome! Let's get it going here. So Hubble's law. Let me start off with probably the most profound picture in all of astronomy. One could argue that this is one of those game-changing pictures. Imagine for a moment that you took a dime and you held it out at arm's length. Okay? And imagine now you're looking at Roosevelt's eye on that dime. Okay? That's roughly the size of the sky that we're going to be looking at. I believe it corresponds to something like 2.4 arc minutes. Okay? So that's the patch of sky we're looking at. Now, to set the stage, imagine we're back in 1994, 96-ish, somewhere in that part of the, I think it's 1996. So we have the Hubble disaster. We get Hubble up and we find out that the lens is blurry. We have the first servicing mission that actually corrects that blurred vision. So it's roughly 1996. Now you have a state-of-the-art telescope that's taken almost a decade to get into space because of the Challenger explosion, and then to correct because of that missed ground mirror. And so you really want to use this thing. And one of the crazy proposals was this. We are going to focus on the darkest patch of sky that we can identify. This part of the sky shows no stars whatsoever. Okay. Now, the risky thing, it was decided to focus Hubble on that part of the sky for a full 10 days. 10 days worth of observations. And you don't even know if there's anything there. Okay? So they take the picture, 10 days worth, and they beam the data back to Earth and they get it all compiled and they process it. And this is what they see. Take it in for a minute. I get goosebumps thinking about it. Maybe you're saying that I'm overblowing it. I'm not overblowing it. This is the most profound picture that I think astronomy has ever seen. Each dot here, pretty much every single blemish, maybe not this one, this one, and that one. Okay, so you see about 4 stars, maybe 5. Okay? But every other dot that you see in this picture is a galaxy. The darkest patch of sky, 2.6 arc minutes. And in this image, there are hundreds of galaxies. Okay? This is the most profound image that I think astronomy could ever produce. It's called the Hubble Deep Field Image, and as you notice, it was released January 15th of 1996. Okay. Whew. Okay. Well, what do you have to do to get a telescope named after you, and why is this image so profound? Aside from the fact that it shows all these galaxies, okay, there's a deeper idea that comes out of this. So we have to go back. Imagine for a minute we're back in the 1920s now. Okay, so we've gone through the Harvard Observatory in the 1880s to 1920s or so. Einstein came on the scene in 1905 and produces his theory of general relativity in 1919. So we're even past that. We're in the 1920s, I think 1926 or so. And there's a great debate going on. Here's the debate. It's between 2 gentlemen called Shapley and Curtis. And the question was, we have an idea about the Milky Way. Okay. We now have RR Lyra stars. It's giving us a sense of where the sun is positioned in the Milky Way. But we haven't yet determined, what about those other splotches? What about M31? Is that an object that's inside our galaxy, or is that an object outside our galaxy? We don't have ways of measuring that distance yet. Okay. There's not a way for us to know. And so Shapley was of the opinion that the Milky Way is everything, that is the entire universe. Whereas Curtis was on the other side of the great debate, that the Milky Way is just simply an island amongst other islands. And the question is, who's right? Edwin Hubble comes in and he produces this photograph. Now, interestingly, I should mention, Edwin Hubble was formally trained as a lawyer, right? He actually grew up, his dad was a lawyer. He went to Oxford, studied law, came back, and actually opened a law office in none other than Louisville, Kentucky. I believe that he could have actually been an athlete, like an Olympic athlete or a professional athlete, chose law. because that's what his dad wanted him to do. Came back to Louisville, opened a law practice. His father died. I believe that's actually what pulled him back into the United States from Oxford. Picked up that habit of smoking a pipe and a British accent, that kind of thing. And then when his father died, he decided, you know what? I'd rather be a second-rate astronomer than a first-rate lawyer. So he went to the University of Chicago to get his PhD in astronomy. And after that, he took up some observation time out west. And I'd have to look up the observatory name. I can't remember for sure. I think it was a 100-inch mirror telescope. In any case, that's where he's at. And he takes this picture of the Andromeda Galaxy. You can see here he's actually noted some stuff on the photographic plate. 1923, October 6th. And he's noting N represents nova. Okay. This is a star that has exploded, but it's not quite like a supernova. And he has another one right here. And this is the one that's really important. That's extremely important. There's a reason why this photographic plate has been preserved. And you notice he scratched out N. He realized he labeled this as a nova and scratched it out. And he put in VAR. What do you think VAR stands for? A variable star. Hubble, in his picture of Andromeda Galaxy, realized that he had an image that contained a variable star. And because of Henrietta Swan Leavitt's work on variable stars, Hubble was able to realize that he can use that variable star to find the distance to Andromeda. You do the numbers, and I don't remember what Hubble actually came up with. I believe he came up on the order, I don't remember for sure, I'll have to correct myself. I'd say 1,000,000 light years. And that was far larger than the agreed upon size of the Milky Way. Boom. He resolves the great debate. No longer is Shapley's position supportable. Okay? It's Curtis. The Milky Way is an island among islands, and M31 is just our neighbor. That's why Henrietta Swan Leavitt deserved the Nobel Prize. Okay? And Edwin Hubble could not have done what he did without that help first. Let's keep moving further. That's probably enough to get a telescope named after you, but he does more. But wait, there's more. And I would argue he was a first-rate astronomer, not a second-rate. So here's a question here. Hubble was actually able not only to measure the distance to the Andromeda Galaxy, but he was actually able to observe a pattern that we now refer to as Hubble's law. So there's two things that Hubble was needed to do. He needed to measure the distance to galaxies, which he actually showed. And the second thing he needed to do was determine how fast those galaxies are moving. So here's a question for you. Review. Hubble's law, the pattern that he observed, relates distances to speed. How do we determine the speed of distant galaxies? Go ahead, take a minute, try to pull that up in your brain. How do we determine the speed of objects in space? You got it? Sweet. A brief reminder for you. We know this as the Doppler effect. Remember that if an object is moving towards us and giving off light, the fact that it's moving towards us will shift the spectra to the blue end, higher frequency. Whereas if the object is moving away from us, the wavelengths will be shifted to the red end of the spectrum, lower frequency. And if we measure the shift, what we call delta lambda, we can actually determine how fast the object is moving, v. Hubble is able to use the Doppler effect to measure speeds of galaxies. Let me give you an example. So what we're looking at, again, horizontal axis, wavelength, and it's in angstroms, 10 to the negative 10th meters. As a reminder, there are 10 angstroms in 1 nanometer. Horizontal axis wavelength, vertical axis, I'll just call it intensity. Okay. And here's the key. This is taken from Galaxy 1832, naming convention, and you notice the hydrogen alpha. Okay. Now, right here is where the hydrogen alpha line should be, okay, right there. Here's where the hydrogen alpha line actually is. It's this huge peak here. And so we can visually get an idea about what the shift is. Pretty cool, huh? As a review, let's get an idea. Using NG 1832, how quickly is it moving away from Earth? Go ahead, pause the video, take a couple minutes, apply the Doppler equation, tell me how fast this galaxy is moving. Got it? Awesome. Okay, let's start off. Remember, we have the Doppler equation. Delta lambda, the change in wavelength, divided by where the wavelength should be, equals the speed of the object, and c, the speed of light. So this, again, is going to require us to read the graph. We need to figure out, where is this line located? Where should it be? Where it actually is. We have to read those two numbers, and that will tell us the delta. Now, again, we're reading off a graph. Your numbers are going to differ slightly from mine, but I read this at about 6605. Of course, where it should be, you see it's slightly over 6560. So I just went ahead and said 6562. It's only now that I start recording that I realize they gave it to you up here, 6562.8. That's okay. I'm just going to use 6562. We can now plug those in. Okay. So the change, I've just taken the difference, 6605 minus 6562, divided by where it should be. So that's the 6562, okay, right where this should be. And that is equal to the speed of the object divided by the speed of light. So we crunch the numbers, and we get something like 0.0066. Incidentally, just to give you an idea, this is sometimes called the red shift. This is called the red shift of the galaxy. How far it is shifted to the red end of the spectra. And I should say a little bit more precisely, the percentage shift, if you prefer. So that's referred to as the red shift. That terminology will come up more. Well, lastly, we have to multiply by the speed of light. 3 times 10 to the 8th meters per second. So we'll go ahead and do that. And at the end of the day, I get 1 million, I guess I say 1.9 million meters per second, right? 10 to the 6th is million. So I get 1.9 million meters per second. For reasons to be seen later, I'm going to convert this to kilometers per second. So I'm going to lop 3 off of here and turn the meters into kilometers. Okay. So there you go. It's about 2,000 kilometers a second. Ballpark, 1,300 miles every second. Now, in the grand scheme of things, that's not very fast. But remember, this is an entire galaxy. That's a big object. Good so far? Okay. So that's a review. That is how Hubble was able to determine how quickly galaxies were moving away from us. Now, here's the next thing. Okay. Hubble was actually able to find a pattern. And here it is. Hubble measured the distance to various galaxies. And notice he's measuring distances in parsecs, million parsecs, 2 million parsecs. In addition to that, he's able to apply the Doppler equation and find out how quickly they're moving away from him. And notice he did it in kilometers per second. So that's why I did ours in kilometers per second as well. And one of the funny things he noticed, and it's already in here, I would have asked you, but he noticed something interesting, that they basically, as you get further away, you're also moving faster. That's weird. We'll have to talk about the underlying model. How can we conceptualize this? Hubble noticed this relationship, and that relationship, that pattern, is known today as Hubble's law. The speed of the galaxy is equal to some constant, the slope of the line, times distance. In Hubble's original paper, he found that the relationship between how quickly the object was moving away and how far away it was located, he found that the relationship was something like 530 kilometers per second per megaparsec. Just to give you an idea, you might say, well, how do we know that Hubble was actually had the right relationship? This is a pretty small graph. Let me give you an updated version of this graph. Here's the updated version. And you notice Hubble diagram for type 1a supernova. It's because of that distance measurement, the 1a supernovas, that we could actually verify Hubble's law to greater and greater distances. To give you an idea, Hubble's original data is this little box in the corner, that little red box. Notice now we're not dealing with 1 megaparsec or 2 megaparsecs. We're dealing with 100 to almost 1,000 megaparsecs. The slope of this line today, 72 kilometers per second per megaparsec. And that's roughly the agreed upon value even today. I say roughly because, as the title of this slide suggests, we actually have two different values. We don't know exactly. We have a couple of different experiments that tell us it's between 70 and 75. And we have a really good experiment that tells us it's between 66 and 68. And that's the problem today. This is a profound issue in cosmology because Hubble's value, the value of Hubble's constant, really determines a lot of extra stuff. So to be continued. So here's another question for you. We'll use the 72 kilometers per second per megaparsec. Okay, that's the value that we're going to use for this class. Okay? Here's a question for you. Using Hubble's law, how far away is a galaxy which moves at 1.97 times 10 to the third kilometers per second? Okay, so we found that using the Doppler effect. How far away is that galaxy? Take a minute, figure it out. Okay, and that's the reason I convert it to kilometers per second, because that Hubble's constant, that 72, is given in terms of kilometers per second. Okay, so I'll have to subscript these. Okay, well, we want to find d, the distance to the galaxy. So I'm going to move Hubble's constant to the other side. Okay, just some algebra. And now let's just plug in our numbers. We're given the speed of the galaxy. We figured that out using the Doppler equation. Hubble's constant comes from empirical results. This is the pattern, the slope of the line in the previous picture, the previous graph. And so we notice we have kilometers per second in the numerator, kilometers per second in the denominator, so those will cancel out. And that megaparsecs, it's a compound fraction, so that megaparsecs will end up in the numerator position. And at least from what I had, just running it through my head really fast, but from what I had, it was something like 27 megaparsecs. I hope that's what you got. Yeah? Good. So let's take a minute and figure out what happened. We took the spectra of the entire galaxy, right? Not just a single star, but the entire galaxy. That allowed us to figure out the shift, which when applying Doppler's equation gives us the speed. We can then apply Hubble's law using Hubble's constant and determine the distance to that galaxy, 27.3 megaparsecs. To give you an idea, the actual distance, 26.5 megaparsecs. How long does it take for light to reach us from that distant galaxy? Go ahead, take a minute, calculate it out. You got it? Good. So we already know the distance to this galaxy, 27.3 megaparsecs. All we need to do is convert that into light years. It's the first step. Let's convert that distance to light years. And so you get something like 87.3 light years. So now here's the question. Remember, light years are a unit of distance. But since we're talking about light, right? How long does it take light from that galaxy to reach us? We can also think of that in terms of time. It takes 87.3 million years for light to travel that distance. In other words, we now have an idea about time. 87.3 million years. So let's think now. That picture, the picture on your screen right now, is not what the galaxy looks like today. It's what the galaxy looked like 87 million years ago. How much further has the galaxy moved in that 87 million years? Go ahead, take a minute, hack it out. You got it? And I'll remind you, we already have the speed of the galaxy. That came from the Doppler effect. We know how long it took for light to reach us. We figured that out using Hubble's law. So we know how fast it's moving and for how long it's been moving for. So we just say distance equals rate times time. The distance that this galaxy has moved during that 87 million years can be determined by taking how fast it's moving and how long it took for us to receive that light. So let's go ahead and plug in our numbers. We have 2,000 kilometers per second. We have the 87.3 million years. And then I've given you how many seconds are in a year. So you see seconds cancels seconds, years cancels years, and we're going to end up with our kilometers. Plug it into the calculator, we turn the crank, and we get something like 10 to the 18th kilometers. That seems like a lot, but it's a drop in the bucket compared to a megaparsec, 10 to the 19th kilometers. Let's go ahead. This is how far it's traveled during that 87 million years. So even though we haven't yet seen it where it is today, we can estimate where it is, right? We know how far away it was, 27 megaparsecs, and we know how far it's moved in that interceding time, 0.18 megaparsecs. So today, this galaxy is located roughly 27.3 plus another 0.2, 27.5 megaparsecs away. So to give you an idea, why do we keep building telescopes? Why do we put space-based telescopes in? What's going on? This hopefully gives you an idea of what's going on. We want a telescope that has a large enough primary mirror to collect enough light from faint galaxies. In fact, that galaxy that I showed you, 11.9 redshift, that is so redshifted that it's almost out of the visible range. In other words, Hubble, which is a visible light telescope, is no longer sufficient for measuring these galaxies. We need a telescope that can measure galaxies that are so redshifted that they emit infrared light. That's why James Webb is an infrared telescope. One reason, to see through the dust. The second reason, because we want to see as high of redshift galaxies as we possibly can. That allows us to see further back in time, closer and closer to the beginning of the universe. Now I have another question for you. Okay? Here it is. Let's assume for a moment that the separation between two galaxies is due solely to recessional speeds. For how long has space been expanding? Go for it. You got it? Oh boy, I can't wait. You see it? I hope so. Here we go. We start with distance equals rate times time. Okay. And we're after time again. We want to know for how long. Okay. So now I'm going to use Hubble's law and replace this recessional speed, right? I say, assume that the distance between galaxies is due solely to the recessional speed in Hubble's law. So I'm going to replace distance with Hubble's equation, Hubble's law. And now I've, of course, exchanged the variables v and v, and you see, hopefully, what's going on. I can cancel out the speeds of these galaxies. No? Remember, let's assume that the universe has been formed and these galaxies are moving away from each other. We use Hubble's law to figure out how long they've been moving away from each other. And the cool thing is, it doesn't matter which pair of galaxies we use. You notice the speed of the galaxy cancels out. You end up with 1 over h naught. I told you, Hubble's constant, h naught, it's imperative that we have a good value of this. This is why. H naught, the value of Hubble's constant, tells us the age of the universe, according to our models. So let's go ahead and get an idea. If I use 72 kilometers per second per megaparsec, I don't like this compound fraction bit. Okay, let's move the megaparsecs and the seconds to the numerator. You have 72 in the denominator. Now I've given you that there's, this is a typo, 3.09 times 10 to the 19th kilometers in 1 megaparsec. So let's go ahead and put that in. Okay. 1 megaparsec is 10 to the 19th kilometers. And I get kilometer canceling a kilometer. And at the end of the day, I end up with 4.29 times 10 to the 17th seconds. If I convert that into years, drum roll. Joy to the world. 13.6 billion years. The estimated age of the universe is 13.6 billion years. Incidentally, why don't we go for this? If the age of the universe is 13.6 billion years, what do you think the size of the universe is? Let me ask you this. What's the fastest thing that you can have in the universe? Light. And how far can light travel in 13.6 billion years? 13.6 billion light years. The estimated age of the universe, 13.6 billion years. The rough estimate of the size of the universe, 13.6 billion light years. I'll let you chew on that. To be continued. Hey, thanks for your attention. I'll see you next time.